In this video, we are going to talk about partial sums for geometric sequences. So what we want to do is we want to find the sum of the first n terms of a geometric sequence. So very similar to how we did it with an arithmetic sequence. But first we know that it's geometric. So we've looked at different types of geometric sequences like this one, and let's say we wanted to find the sum of the first 7 terms of this type of problems. Well, there is a formula, and this formula is just going to be S sub n equals a1, 1 minus r to the power of n divided by 1 minus r. So this is going to be the formula. You don't need to know this formula, but this is the formula that you will have to use to find this. Here, r cannot be equal to 1. And you can easily see that because if you plug in 1 in the bottom, you're going to get 0 in the denominator, which is a no-no. So let's do this example. Notice in relation to the arithmetic sequence, you don't need to know the nth term. You just need to know the first term. You need to know how many terms am I adding, and then the common ratio. So here we want to find the first, find the sum of the first 20 terms of the geometric sequence. And here are going to be my numbers: 7, 14, 28, 56, so on and so forth. Okay, so we want to find the sum of the first 20 numbers, 20 terms of this geometric sequence. So let's write down the formula. We know the formula is going to be S sub n equals a1, 1 minus r to the power of n divided by 1 minus r. Now if we look at what was given to us, we know what the first term is. The first term is going to be 7. R is going to be the common ratio. Let's just take a2 divided by a1. It's going to be 14 over 7, which is going to give us 2. And the number of terms that I'm adding the first 20 terms, so n equals 20. So all I'm going to do is just plug in everything in here. a1 is 7, 1 minus r, which is 2 to the power of 20, divided by 1 minus 2. Okay, and all I would recommend is just put everything in the calculator. So I'm going to take 7, multiply it by 1 minus 2 to the power of 20, divided by 1 minus 2. And what I'm going to get is a really, really large number: 7,340,025. So it's huge. And that actually makes sense, right? Because if you look here, I have 7, then 14, then 28, then 56, then multiply it by 2, I'm going to get 112. Multiply that by 2, I'm going to get 224, and keep multiplying it until I get to the 20th term. Then in that case, by the time that I've done this, I multiplied by 2 20 different times. So I'm going to have a really, really big number. Okay? So this makes sense that this is going to be a huge, huge number. Now let's do one more problem like that. So let's say we want to find the sum of the first 10 terms. And I'm going to have 4, 2, 1, 1/2, and then continues. So here I'm going to use the formula S sub n is equal to a1, 1 minus r to the n divided by 1 minus r. a1 in this case is going to be equal to 4. That's my first term. R is equal to the common ratio, a2 divided by a1. So 2 over 4 is going to give me 1/2. So everything's being multiplied by 1/2. And here n is going to be the first 10 terms, because that's what I'm adding. So I'm going to have S10 is equal to 4, 1 minus 1/2 to the power of 10 divided by 1 minus 1/2. So I'm going to put this in my calculator. 4 times 1 minus 1 over 2 to the power of 10 divided by 1 minus 1/2. And that's going to give me 1023 divided by 128. And if I were to figure out what that is, that's going to be approximately 7.9921875. Okay, that is my answer. Now, so far we've been using this type of problem, but what we're going to do now is I'm going to look at the case of different values of r. So notice that I have, when r, or the absolute value of r, is greater than or equal to 1, as n gets larger, and this means as n approaches infinity, and what I mean is like n gets larger. It just means n gets larger. So if I start adding more and more terms, so I have like a 2, 4, 8, 16, 32, 64. I keep adding everything. I keep adding terms as n gets larger and larger and larger. So if I add the first 20 terms and then I add the first 100 terms, you can imagine that the sum is just going to get bigger. So when we have r greater than or equal to 1, when r is something that's greater than 1, the series, or this type of, the sum gets larger as n gets larger. Okay, so the sum is going to get larger and larger and larger as n gets larger. Okay, now what happens when r is less than 1? Okay, so let's look at this example, this 4, 2, 1, 1/2. The 4, 2, 1, and 1/2. And continues on. So we found out that the sum of the first 10 numbers was equal to about 7.992 whatever. 7.9921875. That's what we figured out. Now what happens when n gets bigger? So would this sum also get bigger, or what would happen? So let's say I want to take the sum of the first 100 terms. Okay, so let's just use the formula again. We know that it's a1, 1 minus r to the power of n, divided by 1 minus r. So a1 is just going to be 4. 1 minus r is still 1/2 to the power of 100, divided by 1 minus 1/2. So let's see what happens as I increase the number. So is it going to get us bigger and bigger and bigger, or is it going to do something else? So I'm going to take 1/2 raised to the power of 100, and then I'm going to divide this by 1 minus 1/2. And what I ended up getting is 8. Okay, and if you have a much fancier calculator than mine, you're probably going to get 7.9999999. Okay, so basically what happens is that as n gets larger, this starts getting closer and closer to a number. And this kind of makes sense, because if you see, these numbers are getting smaller and smaller and smaller. So when I start adding more numbers to the bigger number, this starts, the amount that I'm adding just becomes negligible. So when r is less than or less than 1, the sum approaches a particular number. So let me give you the two cases. And this is what we call infinite series. So here we're looking at infinite geometric sequences. So we're looking for the sum of infinite geometric sequences. So basically what we're doing, what would happen if I add an infinite number of numbers? Okay, well, we know that S of n equals a1, 1 minus r to the n, divided by 1 minus r. Now, as n gets larger and larger, so I put in 1/2 to the 100th power. That corresponds to this term. Well, this thing starts getting closer and closer to 0. So basically, this term is negligible. I don't really care about this term. It's just 0. So when n gets really, really large, this term n r to the n power just goes away. And all I'm left with is this following formula. So S sub infinity is equal to a1 over 1 minus r. This is going to be for the sum of infinite geometric sequences. This is another formula. So I will just tell you that there's two cases. If r is greater than or equal to 1, which is what we had over here, when r was greater than or equal to 1, the sum gets larger as n gets larger. Well, we call this, we say that the sum diverges. That means it gets larger and larger and larger. It doesn't approach anything. If r is less than 1, the sum converges. And how do we find the sum? Here, using this formula. What does it converge to? Using this formula, I will figure out what it converges to. Okay? Okay, so let's just do a problem. Find the sum of the infinite geometric sequence. So here we have 54, 18, 6, and 2. So the first thing that you really want to look at is what exactly is this thing doing? Well, let's look at the common ratio, because if we know what the common ratio is, we can determine whether it's going to converge or diverge. R is going to be A2 over A1. So it's going to be 18 over 54. Okay. So if I take 18 and divide it by 54, it'll be 1/3. 1/3 is less than 1. When r is less than 1, the sum is going to converge. So we know that this is going to converge to something. Now, what is that something? Well, we're going to use this formula. S sub infinity equals a1 over 1 minus r. a1 in this case is going to be equal to the first term, which is 54, divided by 1 minus 1/3. So I'm just going to put this into my calculator. 54 divided by 1 minus 1/3. And what I'm going to get is 81. So as I start adding more and more terms, the sum is going to get closer and closer to 81. So that's basically all there is to infinite geometric sequences. When you're adding all these different terms, you just want to be very careful when you look at the values of r.